Like I mentioned, we're going to look at momentum methods for plane rigid bodies. We're going to consider a plane rigid body as shown here. Draw a little bit better. A little boomerang shape. We'll put the center of mass somewhere here. And then we're going to consider this rigid body being composed of a number of particles with, say, p sub I. And then each particle is going to have some mass, delta mi, and then a corresponding velocity, vi. So we'll draw a point pi here. There's our velocity vi. And then there's a whole bunch of these points all over with whatever velocities they have. From here, we're going to compute the momentum of the ith particle, which is simply just delta mi times vi, the mass of that particle times the velocity. And then from rigid kinematics, we can express that velocity vi with respect to the center of mass of the velocity vcm for center of mass plus the angular velocity of the rigid body crossed with the vector ri, where ri is the vector from the center of mass to that particle pi. And then our resulting momentum is going to be delta mi times the vector vi is then equal to delta mi times the velocity of the center of mass plus delta mi times omega crossed with r sub I. And then that's the momentum of a single particle in this rigid body with respect to that center of mass. It is individual particle mass, so it could vary for each particle. And it is a little bit hand wavy, considering that we consider rigid bodies to be continuous, so there should be an infinite number of these particles. We're going to kind of skip over those details here. We'll see in a moment. I'll continue on that comment in a moment. Okay, so then we're going to compute the total momentum of the rigid body simply by taking the sum of the individual momenta. We use capital L for the momentum. This is going to be the sum from I equals 1 to n of delta mi times the velocity of our center of mass plus the summation from I equals 1 to n of delta mi times omega crossed with r sub I. And if we wanted to extend to some continuous rigid body, we would end up switching to integrals rather than summations. But those details aren't relevant here. Okay, so yeah, first you take the limit as like delta mi and it goes to 0 and n goes to infinity, and then you'd end up with this integral type expression. Okay, for us though, this second term here, this term is going to go to 0. And the reason for that is that for every particle pi, there is going to be another particle rotating in the opposite direction. And as a result, those individual momentums are going to end up canceling each other out. So I'm just going to write that down. So we'll say that this term goes to 0 because for every particle pi, there is a particle rotating in the opposite direction that cancels it out. So rotating in the opposite direction that cancels it out. So we should point out that this is still translational momentum. We will deal with rotational momentum in a moment. Okay, so then we can write here that the linear or the translational momentum is going to be velocity of the center of mass times the sum from I equals 1 to n of delta sub mi, but the summation I equals 1 to n of delta mi is simply going to equal to m, where m here is the total mass of the rigid body. And thus we'll find that the linear momentum or the translational momentum is equal to L, which is still a vector, is equal to the mass times the velocity of the center of mass. Okay, so then the angular momentum of our ith particle, we're going to use capital H here, H sub I. This is going to be equal to Ri crossed with delta mi times the velocity v sub I, which we can rewrite as being equal to, in this case, it's gonna end up being Ri crossed with omega crossed with Ri times delta mi. And under a similar argument that the velocity of the center of mass is going to cancel out as well. Which is why we skipped it here. Okay, so again, we're dealing with plane motion. So since omega is equal to some omega in the k hat direction, again, this is plane motion. We can rewrite the cross products in 33 as r sub I crossed with omega crossed with ri. This is going to be equal to r sub I dotted with itself times omega and then we'll find that our angular momentum h sub I is going to be equal to delta m sub I times ri dotted with itself times omega. And then this is the rotational angular momentum of an individual particle in this rigid body. Okay, so then the total angular momentum of the rigid body is going to come by doing a summation over all of the different particles, and then we're going to find here that h and this is now respect to the center of mass. So the rotational or angular momentum of the rigid body with respect to center of mass is equal to the summation from I equals 1 to n delta sub mi times Ri dotted with Ri times omega, which is simply going to be equal to omega times the summation I equals 1 delta mi Ri dotted with Ri. And this summation here ends up being the mass moment of inertia. About the center of mass. Such that our angular momentum, h sub cm, is equal to the moment of inertia, I sub cm, times the angular velocity, omega. Okay, any questions so far?
I'm a little confused with the velocity of the center of mass. It's appeared a few equations up.
Yeah. Let's come back to that. Let's get through the notes and then come back to that. I don't know that off the top of my head, so we'll go explore. And it might be something I have to go and spend time outside of class to answer. But we'll have a lot of time, so at the end of the notes, I'll try, and we'll see what happens. Yeah, I realized right now that I skipped over that, and so that's a fair confusion. Any other questions?
You said that some of the angular momentum is going to cancel out because there are particles rotating in the opposite direction.
Yeah, we're going to explore that. Yeah, the same question. For the velocity of the center of mass. Because if we come back up here, we start off with this cross product here, and then we expanded v sub I here, and in theory we should be plugging that in here, and then there's no velocity center of mass, and so my suspicion is that it's going to cancel out just like we saw for the rotational part and the translational momentum, and that's what we're going to go and derive at the end of this section of notes. Okay, any other questions? Yeah, I'm pretty sure it's going to cancel out due to the position of these cross products, where the Ri is versus where it is up here. We'll see. We'll go and we'll check. Okay. Any other questions? Okay. All right, so unlike when we dealt with particles with impulse momentum, for rigid bodies we have to consider both linear or translational and angular momentum. And this is going to result in plane rigid bodies going to result in 3 equations. In 3D it will result in 6 equations. But we're luckily right now just dealing with plane rigid body motion, so we're going to get 1 equation in the vertical direction. We'll get 1 in the horizontal direction. then there is a third that is obtained by summing the moments about any point. So I have one obtained by summing moments about any point. It doesn't have to be center of mass. It doesn't have to be a pin position. You can sum about any point you want. Sometimes some points will be more convenient than others, but you can sum moments about any point. If you sum about some point that's not center of mass, then you've got to do parallel axis theorem when computing the moment of inertia. Okay, so we're going to consider a rigid body. Rigid body, we'll put center of mass over here. Just use CM for that. It's going to have a velocity, we're going to write V1 or V2. V1 is going to be at time t1, V2 will be at time t2, and then we'll see where that pops up in a moment. And then there's going to be some angular velocity, omega 1 or omega 2. And then we're going to have some force acting at some position. We'll call the force Fi. It acts at some position Ri from the center of mass. Then we'll also have moments acting on this thing, which we'll say M sub I as well. The moment acts on the entire rigid body. It doesn't necessarily act at a particular point. For rigid bodies, where its location is doesn't really matter. For something like a flexible body, then that position does matter. But that's a higher level class. Okay, so here, we're just gonna write out what everything is. So V1 here is our velocity of the center of mass. At time t1. Omega 1 is the angular velocity. At time t2. V2 is the velocity of our center of mass at time t. Oops, sorry, this should be t1 up here. The first two should both be at time t1, and then the second two are at time t2. Omega 2 is our angular velocity at time t2. F sub I is the ith impulsive external force M sub I is in the ith impulsive external moment. Okay, so we're now at the point where we can go on to define our linear impulse momentum equation. We're going to do it in vector form, then we'll split it into different components. And by the way, when I said vertical and horizontal here, these don't have to be your typical vertical horizontal. They're any two vector or any two directions that are normal to each other inside some plane. You can always reorient your plane so that you have one direction being vertical, one being horizontal. Okay, so in this case, our linear momentum, or linear impulse momentum, or translational impulse momentum is going to be the mass of that rigid body. This rigid body has mass m. It's going to be m times the velocity v1 plus the summation from I equals 1 to capital N of the integral from t1 to t2 of the vector fi d tau, or dt actually, and then that is equal to the velocity or the momentum m times v2. This integral term here, this is the impulse of the ith force. We've previously used a capital I to represent impulse, so we're going to do the same thing here. We're going to say that capital I sub I from 1 to 2. This is our impulse, or the integral from t1 to t2 of f sub I dt. So then we can write for translational impulse momentum, we can write that this is the momentum mv1 plus summation I equals 1 to big N of I, and this is still a vector. This I is a vector term. I sub I from 1 to 2, and that's equal to mv2. From here, we'll split that into our two directions, and we'll get that m times v1x plus the summation I equals 1 to n from I sub I x from 1 to 2. This is going to be equal to m v2x which is then, and then the second equation, we're going to have m v1y plus summation I equals 1 to n of I sub iy from 1 to 2 is then equal to m v2y. So previously, when we talked about summations, I said that there was an infinite number of particles, so really we'd be wanting to do an integral. In this case, there are a discrete number of forces. There's not an infinite number of forces acting on the system, so we are doing a summation here of individual forces. And there's no limits or anything you take here. This is exactly what we should see. Okay, any questions so far? Okay, so for angular impulses or angular impulse momentum, we have two choices. The first is that we can do summation of the moments about the center of mass, and the second choice is we can do summation about any other point. And then in this subcategory, we'll talk about when you have rotation about some point other than the center of mass, such as where something's pinned or so on. For right now, we're looking at cases where there is rotation about the center of mass. Okay, so for choice 1, we can sum about the center of mass. In this case, our angular impulse momentum equation is simply going to end up being I sub c times omega 1 plus, and I guess we should come back up here. This rigid body has mass of m and moment of inertia I sub c about the center of mass. So then we'll get I sub c times omega 1 plus the summation I equals 1 to big N of the integral from T1 to T2 R sub I crossed with F sub I d tau. And so that is the moments created or caused by those impulsive forces, plus then the summation from I equals 1 to P of the integral from T1 to T2. And these should be with respect to dt, these integrals. The moment m sub I dt, which is then equal to moment inertia I sub c times omega 2. Okay, any questions on this? Okay, let's go back to our rigid body, and let's say that we are going to do the summation about some point P instead, and then we'll have a vector from the center of mass, which we'll call RP. In this case, we're going to need to incorporate parallel axis theorem. So we're going to end up with I sub c times omega 1 plus m rp crossed with v1. This is where this parallel axis theorem gets built in, plus the summation I equals 1 to n plus, not plus, of the integral T1, T2 of the cross product of the relative position Ri slash P crossed with Fi dt. I'm just going to go back to my rigid body. This pink vector is that relative position Ri actually needs to go the other way. It's Ri slash P, so relative position of I with respect to P. So those are the moments caused by the impulsive forces, and then plus the summation from I equals 1 to P of the integral from T1 to T2 of m sub I dt. And this is then equal to I sub c omega 1 plus m rp crossed with v2. And then one thing to note, for plane with rigid body dynamics, which is what we're dealing with, everything is in the k-hat direction. After you do cross products, of course. Same thing here.
Choice 2 on the right side, why do we have omega 1 return?
Oh, we shouldn't. That should be omega 2. Okay. So the last one we're going to look at is rotation about some other point than the center of mass. So when the system is specifically pinned, for example, or some other mechanism that forces it to rotate only about a single point for all time. In that case, we can express the velocity of the center of mass. V sub cm is then going to be equal to omega crossed with r, where r is the distance from, or the vector position from the rotation point to the center of mass. So the pinning of this body will remove all translational motion, and then the linear momentum is going to be 0 for all time. We will only have pure rotation. And so in this case, it is just best to sum moments about the pin and then use parallel axis theorem directly in the moment of inertia in order to compute the moment of inertia about the pin. And then we end up modifying impulse momentum. Let me add a page here. We end up modifying impulse momentum in order to account for that. And this becomes, in this case, let me make a modification up here. We're going to say that R is equal to some distance r in the hat r direction. If we're rotating about a particular point, you're going to want to use polar coordinates. That is ideal in this case. And then moment of inertia is going to end up becoming this will be IC plus mr squared. And then for impulse momentum, we're going to get here that I sub c plus mr squared omega 1 plus summation from I equals 1 to big N, the integral from T1 to T2, then of R sub I slash P. We'll just use P to represent the pin position. In fact, actually we'll use O for the origin, because you're generally going to put your coordinate system or the origin at that pin position, crossed with Fi. So that is the moments produced by any forces acting on the rigid body, dt, plus summation I equals 1 to P, the integral from T1 to T2 of the moments m sub I dt, and then this is then equal to IC plus mr squared times omega 2. All right, any questions here? Okay, let's go back to the question from earlier. So I'm going to draw another rigid body. I'm going to put the center of mass over here. I'm going to consider a point right here. We'll call it its position R1. Consider another particle over here. We'll call this R2. So this is particle P1. This is particle P2. And I've chosen these particles such that R2 is the negative of R1. And specifically R1, we're going to say is in 0 in the I direction. We'll just add a coordinate system ij, centered at the center of mass for this case. And R1 here is in 0i plus aj, and then R2 is 0i minus aj. Okay, so previously we wrote that the angular momentum hi, the ith particle, is equal to r sub I crossed with delta m I times v sub I. We're going to add omega for the center of mass, and we'll add a velocity of the center of mass as well, v sub cm. Know that v sub I is equal to velocity of center of mass plus omega crossed with ri. And so then we want to just plug into the angular momentum. hi is equal to r. I'm going to pull out the delta mi. Then it is ri crossed with v sub cm plus omega crossed with ri. Such then that hi is equal to delta mi times ri crossed with v sub cm plus delta sub mi ri, let me rewrite that, ri dotted with itself times omega, and I just pulled that from what we saw previously. I just skipped some steps there. Okay, we're going to focus on this first term. We already know the second term exists. We want to know what happens with this first term. Okay, so we're just going to say that the velocity is cm, or the center of mass. We're just going to say Vx in the I plus Vy in the J, whatever that is. And then omega is equal to, well, we actually don't need omega, so forget about omega. Okay. So first, let's compute R1 crossed with VCM. This is going to be AJ crossed with VXI plus VYJ. This is going to end up being minus A Vx in the k hat direction. You can do the same thing for R2. This is minus AJ crossed with V sub XI plus V IJ. And that's going to be equal to, we'll get J cross I, which is minus K, second minus sign, and then we'll get A Vx K hat, such that when you sum all of these up, they end up canceling each other out. Okay. So you nodded. Does that answer the question on the other side as well?
Yeah. Is that the same thing as earlier? You said it's something in the opposite direction.
Yeah, so just for every particle pi, there is one in the opposite side of the rigid body that cancels it out. Yeah, same thing. Okay. All right, any other questions? Okay.